Hey folks, yesterday we saw spectral theorem. Today I'm going to talk about eigenvector decomposition like I mentioned yesterday, which is called EVD as well, right? So to begin with, we will talk about what's the difference between spectral theorem and EVD, right? The major differences are spectral theorem only applies to symmetric matrices, whereas EVD applies to all square matrices, regardless it's symmetric or not. That's number one, right? Spectral theorem, the other thing is about orthogonality, right? Uh, in spectral theorem, it proves that the matrix will be orthonormal after diagonalization, right? That's what we saw in yesterday's video. Whereas in EVD, it may not be orthonormal, so that's what it means, right? The most important one is the way it's formulated, right? The decomposition formula for spectral theorem versus that of eigenvalue decomposition. That's the major difference. Is in eigenvalue decomposition, the formula is A equal to PDP inverse, right? Whereas in spectral theorem, like we saw yesterday, A is equal to PDP transpose. That's the major difference, right? And the reason why we need inverse in EVD is because the P inverse is required because P is not necessarily orthogonal here, whereas in spectral it is orthogonal, so that's why we do the transpose, right? So that's the major difference, as you can see from the slide. This is just a quick example of calculating the eigen decomposition of a matrix. So the matrix here we are using is 4 minus 2 1 1. Pretty much follow the same steps that we did yesterday while we did spectral theorem. We characterize the equation, we find the determinant. Using the determinant, we solve for lambda, and once we do that, we find the eigenvalues. Once we have the eigenvalues, we substitute the lambda values, which is 3 and 2 in this case, and we find the eigenvectors. And once we find the eigenvectors, the step 3 is decomposition, very similar to what we did in spectral theorem. We do the eigen decomposition, which is A is equal to PDP inverse, right? So we know what the value of P is, we know what the value of diagonal matrix is through what we found before. We do a P inverse, right? And once we do that, we reconstruct and you find the answer is 4 minus 2 1 1, right? So in summary, spectral theorem and EVD are pretty much the same, with the difference of the formula that I mentioned. And this one kind of covers the differences between spectral theorem and EVD, right? So as I mentioned, it applies only to symmetric matrices, spectral theorem, whereas EVD applies to any square matrix, and the other differences here, right? Very similar to what I gave an application of spectral theorem in image processing. EVD in image processing is specifically used for facial recognition. One example of it, right? There are many. Basically what it does is the objective is to reduce the compute power, reduce the storage thing, and etc., right? So basically what EVD in face recognition does is it reduces the dimensionality of the image while maintaining just the important significant features, right? So that you can store it, transmit it, and then what it does is basically while you want the output, it compares the facial image and gives you the output, right? So that's the basic application of EVD. The next video will be on SVD. Stay tuned for that. Thank you.